let me just talk to you on microscopy. Now, when I tell you what is a microscope, or when I ask you what is a microscope, what is the first thing that comes to your mind? You can think of microscope as any device that can give you information which is not visible to your naked eye. For example, the simplest microscope that I can think of is a magnifying lens. So if you look at it, this is the very simple microscope that you can think of. How does this function? What does it do? When I bring a lens close to an object, you know that you see some sort of a magnified image. Now this image that you see is recorded in your retina and you're seeing something in real time. But when I want to save the images, I need to couple this with a detector. So I'll give you an example of the very first microscope that was built. So as you can see here, there's a very small lens at this location and there's a small stage which moves in X and Y direction. If you've seen microscopes in biological labs or during your high school, you must have seen examples of a compound microscope or a stereo microscope. But if you look at the very first version of the microscope, you have a small lens and a sample goes at this particular location here, and then you cannot move the sample in 3 dimensions, but there are only 2 dimensions where the movement of the stage is. So what you have here is the fixed working distance, and you bring an object very close to the lens and you start seeing features which are not visible to the naked eye. Now, if I talk about a general definition of a microscope, I can call any device that can reveal details finer than 0.1 millimeter, that is, you're entering into the micron range, or any tool that helps you get information beyond the resolvable limit of your naked eye is a microscope. Now, if I move further, there is something that I'm using called as resolution. There's a term called as resolution. I was telling you, any tool that aids you resolve details finer than a naked eye. So what do I mean by resolve? So that brings me to the question, resolution, or what exactly is resolution? Now imagine I have a tool and I want to reveal some details. So you're at a distance from me, and if I hold my hand like this, if you're able to distinguish that I have 5 fingers, your eye is able to resolve that there are 5 objects closely spaced here. Now resolution of a camera, resolution of a lens, resolution of an instrument have different definitions depending on the context. Even within a microscope, you have something called as point resolution, you have the information limit, you have the lattice resolution, and so on. To start with, when we look at optical techniques, if I want to broadly define what is resolution, like I was just telling you earlier, if my tool is able to resolve and give me information that there are these distinct objects here when I see through the tool. So, to be a little more clearer, take this particular example. I have 2 close spaced objects here, and if I now use a magnifying lens, if I'm able to reveal the details such that there are 2 different objects here, this is basically the ability of the tool that you're using to resolve the objects. If I talk about resolution limit, there is something called as the Rayleigh's criteria, which is conventionally used for optical microscopy tools. So you consider 2 point objects, and if they are closely spaced and separated by a distance, say rho. So if I see that the point objects have some kind of an intensity distribution like this, which brings me to this image here, the ability to distinguish that these 2 objects are separated by a distance rho is called as the resolution limit. Now, there are ways in which you can derive this. I will not go into the derivation right now, It might come in at a little later stage in the particular course. But when you look at electron microscopy in general, in particular for transmission electron microscopy, if I fit these two point objects or the intensity from the point objects as two Gaussians, and if they are separated by a small distance here, you can look at resolution by the ability to distinguish at the full width at half maxima of this particular peak, or even at the 20% from the maxima, if you are able to distinguish the two objects. This can also be considered as resolvable distance. For example, as you can see, the intensity width here at 20% height is so much, and the width here is so much. Nonetheless, when I'm defining resolution, if I can still see just two objects like this, at a height of 20% from the maxima, and I can distinguish that the centers of these objects are separated by a distance rho, that itself is considered as resolution limit in this particular context. Now, if I plug in all the numbers and get the equation, so by the way, if I was resolving this with a circular aperture and I'm using a light of wavelength lambda, there is something called as the Airy disk, you get something like 1.22 lambda over d as intensity distribution that you get. So if I take such 2 point objects and then derive the equation, I'll get something of this form. So that is how you get your Raleigh's criteria. So in electron microscopes, we are not very much worried about the refractive index here. This mu that you see here and the sine beta, which is a value for your numerical aperture of the microscopes you use in case of an optical microscope. There are ways in which you can play with the refractive index or the numerical aperture. So there are oil immersion lenses, there are different kinds of lenses with various numerical apertures with which you play with the numerical aperture and you improve the resolution. But if I look at this particular numerator of this equation, lambda, for an optical microscope, the wavelength of visible light is in the range of 350 to 700 nanometers. And if I simplify this, approximately the resolution can be assumed as lambda over 2. So I get an average resolution of 500 nanometers when I use an optical radiation. But if I switch to electron microscopes, that is where I'm playing with the numerator of this particular Raleigh's criteria. I can improve the resolution by lowering the wavelength. Now, how do I lower the wavelength? And what is the way in which I can build a tool in which I use an electromagnetic radiation of smaller wavelength is all what forms the foundation of this particular field of microscopy. Initially, people were under the impression that in order to get better resolution and better information from materials, if we switch from visible light to electromagnetic radiation. So in particular, when I talk about electromagnetic radiation, you can think of X-rays, then you have alpha particles, you also have electrons. You can use any of these electromagnetic radiation to start improving resolution if I stick to this particular equation. Now, why only choose electrons then? So if you look at X-rays, the wavelength of X-rays can range anywhere from 0.77 angstrom to 1.54 angstrom, which you are commonly using in characterization. If I use alpha particles, you can also achieve small wavelengths here, but the challenge is the momentum of these alpha particles is quite high. You could use neutrons as well, but neutrons are not charged particles. So looking at all the available options, by the way, there is something called as scanning transmission X-ray microscopy as well, where you are having a lens system or an imaging system coupled with a high energy X-ray source, for example, and you can also use it for getting finer details beyond the optical limit. Now, practically getting lab scale devices with such powerful X-rays is not always possible, and also the lenses that you use to focus X-rays and all is a more complicated construction than the electromagnetic lenses that are used in electron microscopes. And on top of this, being charged particles, you can control the direction and the trajectory of an electron beam by using an electromagnetic field. You can either have electrostatic lenses or electromagnetic lenses, and with all these factors, people were using electrons as the best possible candidates to build microscopes. So initially, it was thought that when I want to improve the resolution of an instrument, so let me just erase this. The mindset or the thought process of improving resolution and getting better and better information was, if you want to view smaller objects, use smaller wavelengths and then go towards electron microscopes. So if you look at the field of electron microscopy, largely from the year when it was invented, which was in mid 1930s to 1940s by Ernst Ruska, by achieving better and better resolutions by improving the accelerating voltages of microscopes, people thought one of the most important aspects or the advancement in microscopy was improving the resolution by going for higher energy systems. There were instruments which were operated at 1 million electron volts or 300, 400, 1.2 million electron volts and so on. Most modern day microscopes are operated with an operating voltage of around 200 or 300 kilo electron volts, and with the advent of what is called as an image corrector, people have started achieving better and better resolution. We'll look at this when I talk about lens aberrations and the construction of image correctors. But that being said, with an electron microscope, with the modern day electron microscope, you can achieve resolutions as low as 0.5 angstrom, or even there are a few cases where people have gone down to 200 or 300 picometer resolution as well. These are some special cases where the chromatic and spherical aberrations are minimized. Now, before I go into more details on electron microscopy and construction of a microscope and the layout of a microscope column, let me just ask you a question. What do you remember about microscopes and lenses? This brings me to some high school concepts that we've all learned. The lens maker's formula, the trajectories that light follows when you're using optical lenses. This is just a brief overview. I'll not go into too many details. If I look at some basic refraction rules for lenses, we all know that when an incident ray is traveling parallel to the principal axis, so here is a schematic of a compound optical microscope. So if I have an object and if I have two lenses, the rays that are traveling parallel to the principal will refract through the focal point of the lens. Now this is how we all start learning and thinking and imagining when I have a lens or an imaging system. Bear in mind that it is not just a focal point, but you have what is called as a focal plane. We'll see that one of the perspectives that you need to change when I think from a conventional optical microscope to an electron microscope is the rays that are traveling are converging not just at a point but at a plane. So you have an array of convergent points at the focal plane of a lens. Next, you have an incident ray traveling through the focal point. It will refract through the lens and travel along the principal axis. So, the vice versa. If I have a parallel ray, it converges at a focal plane. Likewise, if I have some kind of a point object placed close to the focal plane or at the focal plane, it goes through a lens and it follows a parallel trajectory. And the incident ray that goes along the principal axis remains undeviated. With this, if you use a simple geometric construction, you can see here that by using combination of lenses, by placing the object at different distances, you can either magnify or demagnify and form a real image, and then you can also form a magnified virtual image. Here is the most simplest construction of a compound microscope that you can think of. Now, let me just give you a picture. So, looking at a schematic is one thing, but looking at a microscope and trying to understand and bridge a gap between optical microscopes and electron microscopes is what I intend to do in the next slide. So, if I think of an optical microscope, the simplest one, here is an example of a stereo microscope. So, you have the camera and the illumination system here. You have the eyepieces which are over here, and then you have the objective lens here. So, the idea is the light goes through the microscope column. I place an object at this location, and there is some interaction of the incident ray, and when it is reflected from the surface, this travels through the same lens, and you start seeing the object here through your eyepiece, or the magnified image through your eyepiece, or you can record the same information on a camera here. This is one of the simplest constructions where you're using a single lens. So, this is called as a stereo microscope. Now, the example I showed you in the previous case, if I look at a simple construction of a compound microscope, how it looks like is the following. In this particular case, please note that the illumination can happen either from the top or it can happen even from the bottom. Here in this image, you can see that there is a light source placed here. Your samples are placed on this particular stage here, and you have multiple objective lenses on this particular turret here. As you can see, it is written as 20x and 0.45 as the numerical aperture of this particular lens. So, the idea is, if I look at the construction of an optical microscope, in this case your condenser lens is here, and then your objective lens is here. I place a sample at this plane, so when light goes through my object, and then it forms an image by going through the objective lens, and I see whatever information I get on the detector or through the eyepieces which are on top and which are not visible in this particular image. Now, the same construction and the same components that I just mentioned, or the same principle of construction, is what you use in a transmission electron microscope as well. You have combination of lenses, you have a source, you have a condenser lens, you have an objective lens, and you have the detection system with which you form an image and you record the information. Let me do the following. If I flip around this image, before I flip around, let me just clear the animations on here. So, if I compare a transmission electron microscope, which is shown on your on the right side of the screen here, or onto your left side, the same components that I have here. So, I have a source here and I have a source here. I have the specimen stage here and I have a specimen stage here. I have objective lenses here and I have objective lens somewhere in this region. I have a condenser lens in front of the source. I have a condenser lens system here. So if I want to bring a one-to-one correspondence of the optical microscope construction and the electron microscope construction, I just flip around this image, and if I label the components that I just described, here is my source, here is my specimen chamber, and here are the combinations of, so on the left I have my objective lens, and on the right I have my objective and the other diffraction or imaging lenses in this particular system, and somewhere below I'll have the detector. In this particular microscope model that you see here, so this is a lanthanum hexaboride filament TEM, and there's a particular reason why I want to draw this analogy, because if I understand the basic construction and the layout of a microscope, so most commonly the microscopes are like this, which are vertically standing, and the column is such that my source is on the top. There are a few variations or alternative constructions of the microscope possible. For example, so the major manufacturers of microscopes are JEOL, Thermo Fisher Scientific, or Hitachi, or a company called Neon. Most of the commonly available instruments are having a source on the top, but the modern microscopes like TESCAN or Neon, where they are trying to do high resolution spectroscopy, you have an alternative design where the source is on the bottom and the microscope layout is slightly different. It is flipped. The 1 goes towards 4 and 4 goes on the top. Now, going away from that particular deviation, if I go back to this particular image here, the reason why I want to give you this particular layout is when I want to start imaging, I should bear in mind that I should start by doing alignments in such a way that once a sample goes in, I have to bring the specimen to the right height. I have to start with correcting my illumination system. There are various corrections that you will do. We will go to the microscope and see how these corrections are done. And then you start imaging, and if there are any aberrations, you start correcting for the aberrations in the imaging system, and then you start visualizing the data. Here in this particular thing, you have a fluorescent screen here. There's always a confusion when I'm teaching a course. I ask students, when I show a demonstration of the microscope and I ask them, what is the color of electrons? They look at the color of whatever is coming from the fluorescent screen, and I've come across examples where people say that electrons are green in color, which is not really the case. Electrons have a wavelength much lower than the visible limit, so you cannot see them. So what you see in a transmission electron microscope on the fluorescent screen is by the phosphorescence of whatever material is there on the screen, you have emission in the visible range, and in this particular case it is green in color. And in such kind of instruments, the classical old school microscopes, you switch off the lights completely and you start imaging in dark, and you start seeing the features on the screen first, and once you get some meaningful information, you start recording them on a detector system. Modern day microscopes, on the other hand, have what is called as a fluorescent screen camera. So there's a camera placed here at an angle, and the image is formed and you record the image directly on a computer screen. So that being said, this is how a general layout of a transmission electron microscope looks like. So having said that, what can you use these microscopes for? So if you look at it, one main difference in the construction of an optical microscope to an electron microscope is, you see this large columnar structures. Why do we have this column? And what kind of a lens is used in here? And what do we see here? What are these detectors? What is the functionality of all of them is what we'll see through the next lectures in this particular course. So as you can see, first of all, the microscope is built in such a way that you have this columnar construction. The reason why you want to have these columns is electrons, like I was mentioning a short while ago, are charged particles, and you cannot transmit an electron over a large distance, especially these high energy electrons, without deviating too far away from the path of the system if it is done under ambient conditions. You can think of the old school screens, TV screens, where you had cathode ray tubes or monitors, where you have a cathode ray tube and then you have a vacuum chamber and you apply an electrical signal and images are displayed on the screen. And if you put your hand onto the screen, or if you bring your hand, it so happens that the hairs on your hand can stand and stick to the surface of a cathode ray tube. Now, why does this happen? You have the charged particles that are coming out. As an example, even the electrons can hit on the surface of the cathode ray tube, but these are very low energy electrons. Using a similar principle, if I use an electron gun, which is here at this particular location of the emitter, and if I channelize the electron beams along a path, which is this particular path in the electron microscope, if I do not want these electrons to deviate far away from the path, because if I'm doing this in ambient conditions, with the amount of particles that are there in the atmosphere, the particles, the electrons can actually scatter and deviate away from the path. So the complete instrument is isolated under ultra high vacuum. So in order to minimize the effects of scattering and to contain the electron beam along a particular path, we use high vacuum chambers. We'll look at the different kinds of pumps and the construction and the details in a more practical demonstration at the instrument or in the upcoming lectures. But for now, please remember that electron microscopes are ultra high vacuum systems, and the length of this column that you see here is approximately around 2.5 meters, and here is where your specimen goes in. So that is how an electron microscope looks like. And if I move on, what do I use these electron microscopes for? What can I use imaging systems as powerful and as large as these to get what sort of information? So if I move to my next slide, you can see that electron microscopes can be used for imaging. I can get information from features as small as 0.3 angstroms with the modern day corrected microscopes. More commonly, it is 0.6 to 0.8 angstroms, but there are special cases where you achieve this very high resolution as well. And you can use it for measuring and getting meaningful data. What do I mean by measuring? If I look at a micrograph, for example, I see some features, I want to know based on the processing history or based on the kind of sample I'm studying. For example, if I'm looking at a biological sample, what is the size of my cells or tissues, or what are the sizes of my grains and grain boundaries and so on. This kind of an information to build an understanding of what has happened to your sample is what you use these tools for. From the imaging and the measuring together, the information that I get, for example, I can get from an unknown sample what kind of crystal structure a material has. So if I have atoms arranged in some kind of a three-dimensional fashion like this, I know what is the spacing between these atoms that are sitting in a unit cell, at what height are they sitting in a unit cell. So this kind of information that I measure from high resolution TEM or high resolution STEM micrographs, I can feed in and I can create models to understand materials better. This is one kind of modeling and measuring that I can do. These days, you can also do some real-time experimentation in microscopes. You can actually do a real-time heating or a real-time straining or a real-time chemical reaction, and while the features are evolving, you can also measure the changes and you can get some information on the kinetics of the transformations that are happening. Like I was mentioning in the example, you can build more detailed models by getting this information together. I can also manipulate matter. What do I mean by manipulating matter? It can be either by using an external stimulus like electric field or a magnetic field, or simply a heat source and change the sample, or I can use the electron beam itself. For example, if I have two-dimensional materials, these days people are working a lot on systems like MXenes or graphene or molybdenum disulfide, dichalcogenides. There are a host of materials. If I use an electron beam, I can actually shape them, sculpt them, cut the two-dimensional materials, and I can tune the properties of a material. So it is quite interesting on what you can do by manipulating matter. So of course, if you look at the micro processing industry, the electron beam lithography is a well-known system similar to the electron beam lithography, where you achieve about 15 to 20 nanometer resolution. By using an aberration corrected microscope, you can go even down to a sub-angstrom resolution and start structuring the material, especially two-dimensional materials, and you can get some meaningful information. Now, what kind of materials can you study? I'll be very careful when I'm making this statement here. I have written the whole spectrum of all kinds of materials that you can see. I've written metals, alloys, ceramics, glasses, polymers, semiconductors, wood, textiles, concrete, etc. But you can study all these materials if and only if you prepare the specimen the most appropriate way. There are a few limitations on the size of the sample that you can use. I'll come to the limitations of the technique very shortly. If your specimen is prepared the right way, and while it is being interacted with the electron beam in the microscope, I do not have any effects like degassing, decomposition, deterioration of the sample, or interference with the electron microscope vacuum. So under controlled conditions, I can study any kind of a material. The details on how you can study different kinds of materials can be touched upon at a later stage. So if prepared carefully, if you meet all the criterion of how you can see the sample within the microscope, and if you get the meaningful information from this, you can essentially study all kinds of materials.